Welcome guys, my name is Aditya Pawar and let's start our journey to the universe. In this video, we will basically talk about higher dimensions and time, etc., all the axes, coordinates, etc. So pretty much from extending from zero-dimensional objects like a point to a hypercube or hypersphere, or much more higher dimensional objects like a Calabi-Yau manifold, Kähler manifolds, etc. So let's jump into it. Just jump right into the higher dimensions. First of all, we'll start off from zero-dimensional objects to higher dimensional objects. So let's start off from zero-dimensional objects. So what are basically zero-dimensional objects, you may ask? Zero-dimensional objects are any objects which are in zero dimensions. They don't have any dimensions like or any axes to spread in like x-axis, y-axis or something. So basically a zero-dimensional object, an example of it would be a point. Any point you can take, just a point, regular point, or singularity would be an example in a physical solution, but that's mathematical. So let's just continue with the point. Now let's move on to one-dimensional objects. So what are one-dimensional objects? One-dimensional objects are objects which spread only in one direction. So the object which goes in one direction is just basically a line, you could say, as there are 2 points, and if you connect them straight, they became a line. So okay, we got one-dimensional and zero-dimensional object. Now let's move on to two-dimensional object. So here's it's pretty elementary, as we learn in our elementary schools or middle schools, like how to find the area of a square, circle, quadrilateral, rhombus, or etc. So those are some examples of two-dimensional objects. Two-dimensional objects are the objects basically where you start from one point and you should continue onwards towards two directions. So all two-dimensional objects only follow 2D coordinates. And now you would ask the question like, which 2D coordinate should we generally use? So basically in elementary school, you are preferred to say that you have to use two-dimensional Cartesian coordinates. And Cartesian coordinates, by which I mean x and y coordinates, those probably are axes. So yeah, as x-axis is the horizontal axis and y-axis is the vertical axis. So that pretty much makes a graph, and all the two-dimensional objects just lie on this graph, particularly whether it be positive or whether it be in negative direction. You just draw the quadrants and just put on all the objects, and they would particularly come onto the graph. Now from two-dimensional objects, though pretty much middle schoolers or elementary people are sometimes in geometry, in their two-dimensional Euclidean geometry, they face some difficulties, but that's not particularly much hard as we compare to higher dimensions. So let's now move onwards to three-dimensional objects. So three-dimensional objects are very interesting objects, and we live in a three-dimensional world called Earth. So basically what are three-dimensional objects? As from the previous philosophy, if you know that if you take any point and from that point you have to go in three different directions, or mathematically three different axes. So basically also for three-dimensional objects, you just take three-dimensional general Cartesian coordinates, that's it, like x-axis, y-axis, and additional z-axis. Then you can move in three-dimensional space, which is it's just somewhat complicated. So just you are now freely able to move in three-dimensional objects. And what scientists and physicists calculate, like if you are a quantum physicist or if you are trying to find out a particle, its direction or its trajectory, or if you're trying to build a rocket and you have to find which trajectory we should send it, how much pressure should we need it. So basically that's just 3D graph to say, and the fancy word would be just 3D space or Euclidean space or just Euclidean geometry. Now there are different spaces, as this is three-dimensional object, you have 3D spaces. For example, like Euclidean space, which is general conception. Then you have Riemannian spaces also, which exist in three dimensions. If you there's a part of Riemann spaces which basically exists in three-dimensional. And Riemann spaces also exist in 4 dimensions, but then it's a little complicated, just not that much complicated. But yeah, as a physicist, you would have to basically work in 4 dimensional objects. That's it. So I guess that's over with my 3 dimensional review. Though we will separately talk about 3 dimensional and 4 dimensional and onwards as we continue towards the video. So now we will talk about 4 dimensional objects. So 4 dimensional objects, the examples are pretty rare. You don't naturally see them as you live in a 3 dimensional universe. You just know like what direction you're traveling to. As humans, we just know 3 coordinates, from which basically the 2 are just space coordinates like x and y axis, and 1 we would consider time coordinate as according to Einstein, but Einstein reframed it into 4 dimensional space, as basically he said that there are 3 spatial space coordinates x, y, and z, and 1 time coordinate called t. So pretty much that analogy also applies, but from our perspective, we just live in a 3 dimensional universe. So just whatever we do in 3 dimensional universe, that just applies x, y, and t. So now, as we are in the 4th dimension, a pretty complicated and lots of various things out of sight are happening. So to give you some examples, I would say hypercube or half vibrations, or you should take, let's take hypersphere, etc., like various shapes, but they are a little complicated. Yeah, you can take Kähler manifolds or Calabi-Yau manifolds into 4D space. Basically, Calabi-Yau manifolds are just 6 dimensional manifolds at its default set. So yeah, pretty much yeah. So what you do in 4 dimensional space. So basically, if you are a physicist, when you're trying to do some properties in space-time, or you're formulating the Friedmann equations, or if you're formulating the Einstein's field equations, or you're just randomly using tensors and some stuff, then you need 4 dimensional space. And it's pretty much basically said by Einstein that our universe exists in 4 dimensional space. So everything except Earth is in the universe is just 4 dimensional. Like if you remove the planets, just the fabric of space lives in the 4 dimensions, from which I've already explained 3 spatial coordinates and 1 time coordinate. Now we would move to 5 dimensional. Though there are not much things doing in 5 dimensional, it's pretty much like 4 dimensional objects or 4 dimensional space, though you just add 1 more dimension extra. You call them or specify them in extra dimensions. Though for 6 dimension, that would interest some of the string theorists, as their work is basically in higher dimensional objects, Calabi-Yau manifolds, etc., Kähler manifolds, etc. So basically, the default set of Calabi-Yau manifold exists in 6 dimensional space, as it's a pretty complicated structure. Like there are a lot of intersections, it is diffeomorphic, it has lots of things going on, and you can't basically say, oh, so we are going from this plane and we go on to that plane. So basically, if you're a beginner, you just realize it as a Mobius strip, where you only have one path. If you drive along the Mobius strip, you just feel one path connected, but there are 2 geometries. One is hyperbolic geometry and one is spherical geometry or positive curvature. So basically, now to 6 dimensional universal space, we basically take Calabi-Yau manifolds and generally a lot of things, and so that for higher dimensions. So now we will talk about a little in detail about 3 dimensional universe, which we live in, basically our world lives in. So to specifically say 3 dimensional universe, I would specifically state Euclidean geometry or Euclidean space which you live in, which would be represented by e cubed or e to the power of 3, just x, y, and z, basically. But when you're living, that's a mathematical concept for x, y, z. When you're living, it's basically x, y, and t, as you're traveling through space and you're traveling through time also, as you're basically in the human timeline of pretty much 100 years. So basically you're traveling in both directions, so x and y, x, y, and t, sorry, yeah. So basically, now you would say that why do mathematicians take x, y, and z, and why do we general or physicists take x, y, and t? Basically, so physicists, what they do is they are more to nature, or general people generally more are to nature, and like they understand things, or they comprehend things basically, into which basically we see in our general lives. And when you're in mathematical side, it's basically that you're formulating some things, or you're doing trigonometry, you're finding some geodesics, null geodesics on a sphere, etc., etc. So basically like that. So there are two conceptions in coordinates you can take, either the mathematics one, which was xyz, and either the physicist or general life one, which was x, y, and t. So now let's move on to four-dimensional objects. In four-dimensional objects, we can talk a lot about it, but we will not move into the theoretical details like Einstein's field equations and etc. Like which space are we using, and like formulating and stuff. So basically, to generalize all the stuff, I will just basically state that the space we are living in of the universe is currently stated as a flat universe with zero curvature, basically. So pretty much to more summarize you, I will just let you know that there are three main conceptions about the geometries or topologies of the universe. So the first one is flat and zero curvature universe. The second one is basically curved space time, and curved space time with positive curvature. Yes, and the third one is hyperbolic space time with negative curvature. So first space time, you basically, if you have to formulate it, you just spread a flat sheet, in fact, and you just draw two parallel lines, and you are from one point they have to reach another point, like you just have to make a line. So basically in that, as according to Euclid's fifth postulate, the distance between those two parallel lines would be the same no matter how far you go, or which direction you go. They would always be the same, as they are parallel lines in the flat universe. Now moving towards the curved spacetime with positive curvature. For this analogy, we will take an example of a sphere. And if you place two parallel lines on a sphere, you basically know that the the both lines, the distance between them, as it's a sphere, so the curved distance that will take them more in. So basically, you would be curved inwards when those two lines continuously travel on a sphere, and basically the distance between them would be reduced for a positive curvature universe. And now let's come to third analogy, which would be hyperbolic spacetime with negative curvature. For this, you can take a saddle and horse saddle, from where if you put two parallel lines, as you move towards the future, the space between the lines will become more greater and greater and greater. That's the analogy, as both are reversed, as it's basically seen in the hyperbolic geometry. So now we will directly move to six-dimensional objects, as basically there's nothing much. You can just put a simulation of Calabi-Yau manifold to a fifth-dimensional object of 5D. But let's get to the default Calabi-Yau manifold, which is in 6 dimensions. So basically, in 6 dimensions, when you're a string theorist, you particularly calculate, or if you're even a topologist, you basically calculate, or you just work on the properties of spaces, like how's the curvature, how's the isotropy, is the isotropy alright, or is the space homeomorphic, is the space isotropic, and various things. Is it locally connected or simply connected, etc. and etc. Like there are many functions in topology, and it's a bit mathematical and theoretical too, so we will not move on to that concept. We will just go in a general way. So basically to say that you have this Calabi-Yau manifold which is pretty messed up if you see at the first glance. If anyone generally who doesn't know much about physics or mathematics about it just would go crazy like, well, what the hell is going on here? So basically like that. But if you're in the mathematics or physics of it, then you'll probably know like what is going on, and you would be much more fascinated about the object, especially if the object is divided into grids. You will just do isotropy, or you would just do some shifting and isotropy, etc. Basically homeomorphism or etc. So just I guess that would be it for this video. And yes, the time dimension. So basically, if we use time into consideration of four-dimensional objects, as there are two questions mainly, like what is time first of all, and was the time before the Big Bang, or did it get created after the Big Bang? So to the second question, I don't particularly know, or no one else in this world knows, like was it before or was it after? But according to BBN for short, which is called Big Bang nucleosynthesis by Hawking, he proposed that the initial Big Bang singularity was the very starting of all the matter and all the space time in the universe. So that was the initial point of you and me being created, all the universe, all the galaxies and stuff which you're doing. So at that point, before that, there didn't existed either the space, time, energy, or matter. But according to Hawking, it just existed the empty space from which it got created. Though we don't know the process, like how did it got created, but we have mainly views on this hypothesis. So, as according to Hawking's proposal, that he said that according to the initial Big Bang singularity, from then onwards the time got created and the universe started expanding. As our universe is basically, if you're a physicist, as our universe is basically an accelerated expanding universe, and according to the Hubble's law. So basically, I don't have a specific answer for the second one, but I can say for the first one, which is what is time. So time is a thing which is called getting experience in direction, or basically getting experience or aging, basically, to another word like synonym. So time, according to our timeline, which is basically the future, as we humans aren't dedicated to be, or we can't form a formalism which could transport us from the present state or even the future state to our past state, as basically that isn't possible. But yes, we can just go from the present state to the future state, as basically if we analyze it. I basically already explained this in a video about wormholes or something, where I discussed about the light cone especially, and our human life also is like the light cone, just that we aren't able to go into past, we are able to go in future, as our life is basically dependent on positive numbers and positive ages. If we go in the past, we get negative numbers and negative ages, basically what it is, natural numbers. So with that, I guess my talk or lecture, or this was basically an introduction lecture, would be over. And till then, I would see you guys. And yes, once again, sorry for, and I apologize for being so much late, as my last video was like 4 or 5 months ago. Like, it's been a long time. I know you guys would have been like, why isn't this guy posting any videos? Yeah, I know it's been a long time, and I've came back again, and the reason was that I had my annual exams basically. So yeah, pretty much explains it. And yeah, I'll continue my videos and lecture talks, and also yeah, you guys can also comment below like which video should I make on next, as this video too was a comment made by a person who said that could you make a video. So yeah, this is a request video, so yeah, I can do that few times. Until then, farewell mates.